Howdy, today I'm Flipping Science, we're looking at atomic spectra. The science understanding that we're looking at today is that the emission and absorption spectra of elements provide evidence that electrons are arranged in distinct energy levels and can be used to identify elements. So just recapping atomic structure, last video we looked at how the nucleus is made up of protons and neutrons that are found in the nucleus, and how are the electrons arranged. So the electrons are arranged in shells of electrons spinning around really quickly, and the question is, how did we figure that out? So Niels Bohr is this guy down here. He was a famous chemist and physicist. He was working on atomic structure around about the same time that Rutherford was working on atomic structure. Now, Rutherford figured out that the plum pudding model wasn't accurate because from his gold leaf experiment, he found that there was that dense nucleus that was positively charged. What Niels Bohr was looking at, he was looking at spectra. So when you heat up or excite a gas, it gives off light. And that light comes out at several distinct bands. And Niels Bohr was the guy who figured out why that was. So if the electrons were just scattered around at random around the nucleus, you would get just a rainbow of light coming off of every element when you heated it up, or every gas when you heated it up. But because there were specific bands, he figured out that that must mean that the electrons that are producing the light have to be in specific locations. So he called those energy levels, or now we kind of refer to them as shells. So he said that the electrons have to exist in specific shells, and that led to a change in the model of the atom called the Bohr model. So now you have a nucleus in the middle, which is still positive and contains protons and neutrons, but around that you find the electrons in distinct shells. So they can only be in these places, they're not randomly scattered around the atomic radius. So how do the shells explain that spectra of light? When you add energy to atoms, so you heat them up or you run electricity through them or you excite them, which is the term that we use for both of those processes, the electrons can move from one energy level to the next, so from one shell to a shell further out. Normally, electrons prefer to be in the lowest energy state possible, which is occupying the smallest shells, the shells closest to the nucleus. When you add in energy, they jump up a step. They don't like being up here, that's unstable. They want to be in the lowest energy state that they can. So the electrons jump back down, and when they jump back down, which is what's happening down here, they release a piece of energy called a photon. So a photon is a packet of energy. That energy can correspond to light that we can see, but it can also correspond to other energies as well that we can't see. So here's hydrogen gas. If you put energy through hydrogen, you get this kind of purpley color coming out of it. That purple color is made up of these distinct bands. So there's a red band, a green band, a blue band, and a violet band. If you add those together, you get this purpley color. Each of these bands corresponds to electrons jumping back down from a higher energy state. And when that happens, they give off a photon. Lots of atoms giving off a photon at the same time, you get lots of these little color bands coming out. These color bands, you need to pass them through a prism to be able to see the specific color bands. You see the mix if they're all together, but if you pass them through the prism, then they break up into the specific bands. So we'll just explain that one more time. So here we have an atom, you put some energy into it by heating it up or adding electricity. Electron in a lower energy state goes into a higher energy state, so that's called the excited state, but that's unstable and it pretty quickly falls back down. When it falls back down, it gives off a packet of energy equal to the energy gap between here. You can put energy in and you can see what's called an absorption spectra, which we'll talk about in a second, and so you kind of see black lines where the atoms are absorbing that energy. And you can get emission, which is where the electrons fall back down. So if they emit, then you just see the specific bands. So there's an absorption spectrum and an emission spectrum. So I'll just talk about them again later. If we go back down to hydrogen, the colors that you get for hydrogen are from specific jumps. So this red over here comes from this jump from the third energy level down to the second. This blue band here comes from the fourth energy level going down to the second. This blue one comes from the fifth energy level going down to the second. There are other jumps through here, but we can't necessarily see them because they're in the infrared or they're in the ultraviolet up here. But these ones we can see, and that makes the purple color of the hydrogen gas when you excite it. Let's have a look at some spectra. This one here is a very simple spectra from the sun. It doesn't show all the detail, This is a less detailed version of this one down here. You can see how complicated this one is. But if we look at the light coming from the sun, we can see that there are matches to bands for some elements. So here's hydrogen. We can see that this red band here matches up with that where that red band there would be. This blue one here, that purple one, and so on. So that tells us that there must be hydrogen in the sun. Another gas that was discovered from the sun is helium. Helium is this band here. Now this band doesn't line up because this one might be a bit dark, but this yellow one does. So we get this band here that isn't present in any of these other elements that we're looking at, so that tells us that helium is in the sun. And that's how helium was discovered originally. From looking at the spectrum of the sun, they found this band that didn't match hydrogen, so they said that must be a new element called helium. Next one we'll have a look at here is mercury. So if you have a look at the mercury bands, you can see none of those really match up to the sun. And there's a reason for that. You don't find mercury in the sun. Mercury is too heavy to be produced from the fusion process that happens in a sun like ours. You only really get up to iron. So you don't see mercury, any of the bands matching up for the sun. Down the bottom here we have uranium, and you can see uranium has a lot of bands, and one of the reasons for that is there's a lot of electrons in a uranium atom because it's quite big. So we get a lot more bands. And again, none of those will really match up with any of the spectra from the sun because uranium is too big to be produced from the fusion process in the sun. This picture here is an absorption spectrum of the sun in a lot more detail than this one here, so using a lot more finer prisms and so on. So using all these bands, we could identify specific elements that are present in the sun. And like I said before, you only get up to iron. Anything above iron we can't find in our sun because it's just too heavy to be produced from the fusion process in the sun. So as I mentioned before, there's two types of spectra that can be produced. There's emission and absorption. Emission is when you just heat up a gas, you pass the light from that gas through a prism and that breaks it up into its lines. So you see specifically coloured lines against a black background. That's an emission spectrum. An absorption spectrum is when you you're really passing white light into the gas. So the white light contains all the colours of light, so we have up here the continuous spectrum. As that passes through the gas, some of the photons of the white light excite the electrons, so they get absorbed by the gas that you're passing the white light into. So instead of seeing coloured lines on a black background, you see black lines on a coloured background. So that's an absorption spectrum. So this is how we look at the sun, for example. If we're looking at a spectrum of a sun, or a star of a sun, we're looking at an absorption spectrum. So I've already talked about how helium was discovered by looking at the sun's spectrum. Some other elements have been discovered by using spectra as well. So Bunsen and Kirchhoff, Bunsen of Bunsen burner fame and Kirchhoff, these two guys down here, they looked at spar water. So they heated up spar water. They heated it so much that it turned into a gas and got light out of it. And when the light came out of it, they again used prisms to break it up into its bands. And they found two new elements. So one of them was cesium. So here's cesium down here. So the bands from the spar water, they didn't match up anything else that they had found before. And the other one that they found was rubidium. So rubidium and cesium were found by looking at the spectra from this spar water. So what else can we use spectroscopy for? Spectroscopes are often attached to telescopes, so telescopes that look at distant stars. And the reason why we do that is so that we can see what the stars are made up of. So by looking at the spectrum that's produced from those stars, we can say, if it's heavier in one element or another, or if it contains bigger elements than our sun does, for example. What's very interesting now is the telescopes are getting so good that we can use the light from a star that passes through the atmosphere of a planet in front of it, pass that through a spectrograph, and we can get some lines. Those lines tell us what kind of elements or gases are found in the atmosphere of those planets. Now this is very new technology. It only started being used in the 1990s or so. But by using this technology, we can say, for example, that a distant planet has a lot of water in its atmosphere, or a lot of nitrogen in its atmosphere, or a lot of potassium floating around its atmosphere. So this is a very interesting development because it means we might be able to determine which planets that are really, really far away are similar in composition in terms of the atmosphere to Earth, which is an exciting development. So today on Flipping Science we looked at how the spectra of gases help determine the structure of the atom, and also how using those spectra helped us to determine there were new elements. That's it for Flipping Science today. See ya.